Um, so we have a problem session this afternoon. There's a problem set due this week, and there'll be another 2-week assignment coming on Wednesday. So, last time we had developed a fairly complete picture about thinking about the energy levels of atoms. And the picture that we developed in thinking about the description in terms of how we thought about atomic structure, sort of in summary, is firstly, we have the mean field approximation. And in the mean field approximation, the potential seen by each electron is the average potential seen by all of the other electrons plus the nucleus. And one then looks for solutions self-consistently in such a way that one, for example, for the ground state, minimizes the energy. And in doing so, then each electron is assigned an orbital. So it's a kind of independent electron model, but it's not exactly independent because the particular orbitals that the electrons find themselves in depends on the state of all the other electrons. But this kind of approximation leads us to some kind of what we call electron configuration. And in that electron configuration, we have, some number of electrons in some orbital, and some electrons in some other orbital, etc., depending on the number of electrons, and that those particular orbitals we found based on the Hartree-Fock approximation, and it would then give us some numerical equations for those radial wave functions. The mean field approximation, as we just described again, is this kind of each electron has its own wave function. Now, of course, we know which electron's which, and we have to anti-symmetrize completely in order to be consistent with the Fermi statistics, but there's a kind of, each electron has its own kind of quantum. We then went beyond that and discussed corrections to that term. So, the Hamiltonian for the system involves the kind of single electron description, which is our sort of separable approximation here for these mean fields, and then corrections, the corrections being due to corrections that depend on all the electrons. And this was our non-central field correction. And then, of course, we have things like spin-orbit coupling, and if we wanted other relativistic corrections. And so what we discussed last time was how we can then think about these additional terms as perturbations to this description. And depending upon which of these terms dominate, that determined, in some sense, what the good quantum numbers were that described this many electron state, this many electron wave function. And we didn't actually calculate what those strengths of those perturbations were, but we described, depending upon which of these perturbations were big, what the effective good quantum numbers of that describe this many electron state would be. At this level of description, all we really know is the only really good quantum number is the total angular momentum, J, and then some projection along some axis. But what the other good quantum numbers are depends on the level of description. In this, what we had, of course, our good quantum numbers here were the individual electrons each have good quantum numbers. It's kind of a separable approximation, right? This Hamiltonian commutes with the total angular momentum. So with this level of description, the good quantum numbers are L, M sub L, S, M sub S. And then if we then thought about this as a perturbation, well, let me just say, in this system, the good quantum numbers are the J sub i's, M sub J sub i's, and L, S. So if we then combine all of these different perturbations together, depending upon the order we do them, depends which good quantum numbers we describe those states with. If this term dominates, then, well, I'm sorry, let's start with this. If this term dominates, then what we say is the coupling is Russell-Saunders coupling, sometimes known as LS coupling, because the capital L and the capital S are the good quantum numbers. And then we then couple together L and S through this perturbation to get the total angular momentum J. Alternatively, if this is a stronger effect than this, then first we couple the individual L's to the individual S's to get the individual J's, and then the J's are coupled together to get the total J, and that's called JJ coupling. So you'll see in the atomic physics literature, one talks about LS coupling versus JJ coupling. For most of the atoms we deal with in sort of modern atomic physics, as reason we'll describe in a moment, I mean, I've never dealt with atomic spectra which are JJ coupled. It's just not something I'm familiar with, because it's rare, you know, this is not the atoms that we laser cool, for example. They would have to have quite big nuclear spins, not nuclear spins, nuclear charges, so that the electrons are moving very fast, and then you have many such electrons. So, you know, if we're going to laser cool lead, then maybe we have to think about JJ coupling. But it's just not something I'm particularly familiar with. So the description that we had here, just to remind you, so now I have this idea, the configuration. And then the different configurations with different, basically, M sub L values and M sub I values are coupled together to give a total L and S. And that splits out to give us quantum numbers that we call capital L and the multiplicity 2L plus 1. And then these individual levels are split up due to the fine structure, or the spin-orbit coupling, and we denote these in terms of the multiplicity, the total orbital angular momentum L, and then the total electron angular momentum, which is the combination of L and S. And of course, if we have nuclear spin, then this is further split up, although there's no extra subscript that's typically given in these things, but we would give it an F, where of course F is the total angular momentum of the atom, including both nuclear spin as well as the total electron angular momentum, J. So these are what we call terms. This is fine structure. And hyperfine structure. And as we discussed, for given configuration, there are the Hund's rules, which tell us sort of the rule of thumb about how these things are split up in terms of the total orbital angular momentum and the total spin angular momentum of the collection of different configurations of the atoms. Okay? Of course, what the final thing we showed in the context, if we are looking at a particular case of a closed subshell, then as we discussed last lecture, the central potential is a perfect approximation to the Hartree field equation, Hartree-Fock equation. Hartree-Fock is 1 with central field, in which case there are no such corrections. Moreover, the term in that case, the only term that's possible, because in a closed shell, you have all possible m sub L values and all possible m sub S values. The only possible projection of angular momentum is 0. So in the case of a closed shell, we have L equals 0 and S equals 0, and the only term that's possible is the singlet S0. Okay. So, anybody have any questions about any of that? All right. So, we're now going to say, all right, there's some atomic structure. The atomic structure is whatever it is. It's denoted by certain quantum numbers, and we'll revisit what those quantum numbers are when need be. But we'll just take it as, you know, the beginning now. There's atomic structure. It was handed to us somehow. And now what we really want to do for the remainder of the semester is think about the way in which we can manipulate atoms by interacting them with external fields for fun and profit. And so, in order to do so, we want to think about the interaction of these atoms with external fields. We've peeked at this a little bit with the Stark effect and a little bit with the Zeeman effect, but we want to do so now a little bit more systematically. And in particular, our goal is to think about absorption and emission of light by these atoms, and moreover, the coherent interaction, quantum coherent evolution associated with the coupling of electromagnetic waves to atoms. So let's just think about that for a second. And let's think about the question of absorption and emission. Well, I mean, we have this fairly complicated description. We're thinking about a general atom. In the case of hydrogen, well, that's a reasonably simple thing to think about. If we had hydrogen or more generally, a one electron atom or ion, get exactly one electron down to the nucleus, well then the description is fairly simple, because the act of excitation or emission is changing the relative coordinate of that electron relative to the nucleus, and then looking at excited orbitals of that one electron. So in this case, the description of absorption and emission is the transition between orbitals of that electron. But if I start thinking about multi-electron atoms, like rubidium, well, how shall I think about that? I have lots of electrons in that case. And the excitation in general, one might have to consider a new mean field approximation in terms of how all of the electrons are adjusting themselves when I now have a photon in the problem, in addition to the Coulomb interaction. And that's a fairly complicated business to try to treat. I mean, that, you know, a lot of modern atomic physics theory is really thinking about how you truly take into account when I have multi-excited system, how do I really treat that many-body problem? But for the most part, we can skirt a lot of those complications, because if I think about that, if I have a closed shell, that in that closed shell I have very tightly bound electrons. And if I'm thinking about absorption and emission by light, typically the amount of energy, you know, in a few eV of an optical photon is not going to be enough to take one of these electrons in this closed shell, in this singlet S0 closed shell, and excite it. So I can think about those electrons as essentially inert. And one talks about, one divides the electrons typically for absorption and emission. One divides the electrons into two classes. The so-called core electrons, which are the electrons in the closed shells, and what are called optically active electrons, which are the electrons in the last subshell. So the idea then is we think about although in principle there is a complicated many-body problem associated with the interaction of the collection of electrons, the nucleus, and the photons that are present, one simplifies the problem by thinking about the dividing up the electrons, and the electrons that are in the closed shell are essentially inert. They're not excited, they're just They are sitting in the core down to the nucleus and are basically passive observers to what's going on. Whereas the electrons in the open or the last subshell, in principle, depending on how much energy one has available in your laser or lamp or sunlight or what have you, those electrons are the ones that can be excited. And we think about them in terms of whatever these configurations are. Now, the situation is even typically a little even more simple than this, which is that typically, even if I have multiple electrons in the last subshell, typically the configurations that are excited and accessible are the ones where only one of those electrons is excited. So if I had some ground state configuration, like say the 2s squared configuration of beryllium, or the, well, we know in the 1s squared configuration of helium, in fact, it's only possible to have a bound state with only one of the electrons excited. If both of the electrons were excited, that's already in the continuum. So typically, it's only one electron of these in this last subshell, which is optically excited. Although not always. I could have, in beryllium, there are configurations with both excited, and they can go down to other lower lying states with both excited as well. So our description will be thinking about exciting these optically active electrons. And what we'll study then is the absorption and emission of light, thinking about it as the excitations of these optically active electrons in the atom. Okay? So within that context, the simplest of atoms to deal with are the ones that have exactly one optically active electron. So the simplest atoms to manipulate via absorption controlled, put that in parentheses, don't necessarily have to control it, but ultimately that's where we want to go. Absorption emission are the group 1 elements of the periodic table, because the group 1 elements have one optically active electron, period. And those, of course, are the alkali metal atoms. So they have simple configurations. Their configurations are very similar to hydrogen. Of course, hydrogen is group 1 element, not quite an alkali metal, but still group 1. Right? It had its configuration is 1s. Then we have lithium, which is, let's say I never remember the order of the, there it goes, neon. Okay. So we have the helium core, and then a 2s electron. Then we got sodium, which has the neon core, and a 3s valence electron. Potassium has the argon core and a 4s valence electron. Rubidium cesium xenon core and a 6s valence, and francium, which is the radon core and 7s. Okay. All of these atoms have been laser cooled. All of them have been condensed all the way to BEC, I think, other than francium. Francium is the only one of these whose only has all of its isotopes are radioactive. But that's actually interesting too. I mean, there are some very long-term interesting experiments in studying laser-cooled and trapped francium, because it's a way in which one can make detailed structures of nuclear physics by trapping collections of, say, francium atoms and looking at the spectra and how they are modified by nuclear forces, like electrowave forces. So the alkali atoms are our friends. They are our friends because of this simple structure, because they have exactly one optically active electron. It means it's easy for us to manipulate them, because that one electron also typically is not only is there just one electron, but it's not going to be that tightly bound, which means that the excitations require not a lot of photon energy, which means that the excitations can be obtained with laser fields that are not heroic, infrared or visible light, as we'll discuss in a moment. Now, the fact of this atomic structure means that as you're studying your homework right now, the energy level structure of the excited states, these are all, of course, the ground states. This configuration is the ground state of these atoms. The excited states are similar, have the same kind of, certainly they have the same quantum numbers as hydrogen, because we just have one electron. We don't have to worry about JJ coupling versus LS coupling, because there's only one kind of coupling. There's one L, there's one S, there's one J, period. But the excited, let's just write down a few things. The excited states of alkalis have similarities with hydrogen, but some important differences. And those differences are the ones you're looking at right now in your homework assignment, problem 3. And it's quite easy to understand this. And if I look, just make a little sketch, which I'm going to copy out of Chris Book's book, because I think it's a nice little picture here. So here's just a sketch of the probability density of my electron cloud. Look for, say, sodium. So I have some collection of the core electrons, which make some probability density here. This is as a function of the radial distance. And these core electrons then, as we've discussed, shield the potential energy associated with the attraction to the nucleus. And the amount of shielding that this outer electron sees, in this case the 3s electron in the ground state, and then excited states, will depend on how much those that outer electron, that valence electron, penetrates into the core and then sees more of the nucleus. Yes, sir?
Is there any of the alkali atoms where if an electron off the shell is excited, the energy is still below the first ionization level?
It's a good question. I think the answer is yes, but honestly, I don't know. I believe the answer is yes well, what I'm thinking about, which you may remember as well as I, is so-called Auger processes. It's something you learned about in your modern physics course somewhere. You've heard that term, maybe. And the Auger processes are when you have these auto ionizing processes whereby you excite the system and then it lowers and then ejects one of the electrons. And that's my guess of what happens in these kinds of situations. And I believe what that means is that those excited states are actually above the ionization level. But I'll double check that. I don't know the answer to that.
Yeah, but probably it won't matter very much if we just want to study the upper level.
Well, indeed. I mean, there is a question as to whether what are bound states and what can be excited in a, say, if I wanted to coherently excite and coherently de-excite. I'm pretty sure, just from my cursory view of the spectra, that those kinds of states are in fact not below the ionization level. I think they are auto-ionizing. They are not, you could not just de-excite without coupling also to the continuum, but I'm not sure about that. But let's look at these lower energy levels in the moment, the ones in which the core is inert. Well, let's think about just the ground state for the moment. The ground state has got this 3s electron. Remember, n equals 3 means n sub r plus L plus 1 equals 3. Okay? So if L is 0 and the principal quantum number is 1, that has 2 radial nodes. So it looks kind of like this. This is my 3s orbital on top of the core. Whereas if I looked at something like, here's the core again, and I looked at the 3D, it looks kind of like this. So the point here is that the lower angular momentum orbitals penetrate deeper into the core because they have a smaller impact parameter because there's less angular momentum barrier, and therefore they see more of the nuclear charge, and therefore they are more deeply bound than the higher angular momentum orbitals with even the same principal quantum number, whereas we know in hydrogen we have this kind of accidental degeneracy. Okay? So the point here is that the lower, for a given n, the lower angular momentum orbitals correspond to more deeply bound states. It turns out that in the case of alkalis, the energy levels are well approximated by a small modification of the Bohr formula, basically, or the formula that we get exactly out of the Schrodinger equation. Now, of course, it's still spherically symmetric, so my energy levels don't depend on m sub L, but now they do depend on both n and L. But they do so in a fairly simple way. So this is in atomic units. When we had hydrogen, we just had minus a half times 1 over n squared, and being the principal quantum number. Now we have a modification of it by an amount that depends on L, and that little correction is what's called the quantum defect.
Your two pictures up there, should I be taking it seriously that the 3D peak is closer than the 3S peak?
I think that's true, actually. Yeah, I think that's true.
It's kind of weird. All right.
Yeah, it's the trade-offs between n sub r. This one has no radial nodes because it's n equals 3. Nonetheless, this one is much more tightly bound because it sees more of the nucleus. Okay. So this is an approximate formula. It's not exactly right because if you were to try to write it as a quantum defect, really the quantum defect has a dependence on n. It's not really exactly just for a given L, there's a quantum defect, but it's not a bad approximation. I think particularly for the lighter half-lives. So sometimes this combination is written as n star, where n star is not an integer. So what this means is that the spectrum does no longer have a degeneracy in L the way we had in hydrogen. And if I make a little sketch here, copying that picture out of Chris Foot's book, -1, -2, oops. Are we okay?
Yeah, yeah, yeah.
Sorry about that. Let's try again. Okay, try to draw this picture. Okay, so what am I drawing here? This is the energy of the excited states, or actually all of the states, depending upon N and L. This is the series with all the different excitations with L equals 0, L equals 1, L equals 2, L equals 3, etc. And this then is, so this is the 3s, this is the 4s, this is the 3p, this is the 4p, this is the 5s, the 4d, the 3d, there's nothing over here, but there is. Sorry, this is, I thought this was just 4, 5p, 4d, 4f. Okay, so what do we see here? Well, what we see firstly is the quantum defect depends on L. And once I start getting to a high enough angular momentum, when L gets to be 2 or 3, by that time the quantum defect essentially disappears. Because if you have such a big angular momentum barrier, you don't see penetrate into the core at all. And at that point, it should look like hydrogen. Because if I have Z minus 1 electrons in the core and a nuclear charge of Z, it's like I have a proton sitting there. And outside this spherically symmetric shell, it should basically asymptote to hydrogen. So for this case, the quantum defect for sodium, this is for sodium. The quantum defect for sodium is about, for the S states, it's about 1.35. For the P states, it's 0.86. For the D states, it's approximately 0.001. And for L greater than 2, it's approximately 0. So in an alkali atom, the main excitation, the optical excitation we care about, is this excitation from the valence electron going from whatever n-s state up to the np state. And this is typically on the order, this is an optical frequency. So, furthermore, to just get a handle on all the notation, if we're talking about, for the case of the alkalis, we have one optically active electron, which means that the term are trivial. It also means that the notation is confusing. What do I mean by this? Well, I can specify, because the core is fixed as a singlet as 0, everything is about the valence electron. So the configuration is specified by what's going on with the valence electron. It has an end of L. And then, well, there's only one possible term, because the total orbital angular momentum is the angular momentum of that particular electron. All the other ones, their total angular momentum was in the core is 0. So the term here has L, where L equals L. And then what is the multiplicity? Well, there's one electron. The other ones are all paired up into 0. So 2s plus 1 is what? 2, because s is a half. And then I can have j, where j can be either L plus a half or the magnitude of L minus a half. So there's two different ways one sees this. One can talk about J-J coupling is the same thing as LS coupling. It can first couple the orbit to the spin, but there's only one electron. So sometimes you'll see these things, the electrons written this way, or you'll see the term. The little letters are for the individual electrons. The big letters are for the terms, but they're the same thing. But you'll see both notations. So sometimes you'll see it as little 3s 1/2, and sometimes you'll see it as big 3 big S 1/2. They mean the same thing because there's only one electron. So let's just to get a feel for these, because it's important to see what these spectra look like. These are the atoms we're generally dealing with. So the spectrum near first excited state of all the alkalis. The ground state has an ns orbital, and it's a doublet s1/2, right? Because J, in this case, is the same thing as the spin, and that's 1/2. Oh, by the way, quite often in the context of alkalis, it's rarely the case that we bother writing down the multiplicity because there's no distinction. It's not like in helium where you have triplets and singlets and you have to worry about it. They're all the same. But we'll just write it down now. And then the first excited state is NP, whatever that N was. You know, either for rubidium it's 5. And then this gets split up into, well, of course we know it's a doublet P. Different two notions of the term doublet, but we also can have J equals what? Well, L is 1, so we can have J is equal to 3/2 or 1/2. And they're split by the fine structure splitting, which is due to spin orbit. So this transition and this transition are split, and they have some arcane names. This transition is known as D1, and this one is called D2. It's a crazy, stupid notation, but it still persists. We always talk about the D1 line and the D2 line, because in old spectroscopy, for example, in sodium, one saw that the line was split into a doublet, D for doublet. Has nothing to do with this doublet. It's a different sense of the term doublet, and so D stands for doublet. It has nothing to do with L equals 2 or anything. It's just, you know, Sanskrit, and we're stuck with it. So when talking about the D1 and the D2 lines of alkali, they're important transitions. Then, of course, in addition, we have in the alkalis, all of them have non-zero nuclear spin. So there's also nuclear spin I. And because of that, we split up into F. And what are the possible values of F? F, of course, is equal to the sum of I plus J. And the magnitude of F goes from the magnitude of I plus the magnitude of J to the absolute value of the differences. In this case, J is 1/2, so I can have F equals I plus 1/2 and I minus 1/2. Similarly over here, this is my F. And for the P3 halves, I can have 4 F values. I plus 3/2, I minus 3/2, plus 1/2, I minus 1/2, depending on the value of I. So that's the spectrum we're going to get to know and love. and live with. And it's all of modern quantum optics experiments are done on atoms that are done with atoms that have this kind of detector. Most of them, not all of them. Yes?
How does this picture change when you have a single ion, like, calcium? Because
You mean
there are lower lying D states, right, which you always have to repump out of,
Uh-huh.
which is a pain. So where does that come from?
Well, I mean, so that picture is, the picture is that we don't have the closed core in the same way. So there's interaction between that valence electron and the core in a different way than when it's an inert neutral core.
So the shape of the core changes when it's charged.
It's not just pure central field anymore. I don't really know that much about those kind of atoms,
Right.
because they're ions. But I should. And of course, the picture changes when we're not talking about group 1, but we're talking, say, about group 2, which was my other caveat about lots of experiments now are done with group 2 atoms. They're more complicated because they have these 2 electrons in the valence outer shell, and so you have the singlets and the triplets, as well as how whether the d or how well I just erased it, but the way that quantum defect works is very different. Yes. Right. So just for fun, just to get a sense of how big, I should say the fine structure splitting, the spin orbit coupling in spin orbit coupling is a big effect in the alkalis because, well, those electrons, especially in the higher, things like cesium, as we'll see in a moment, huge fine structure splitting because those electrons are whizzing around pretty fast. So just to remind you, or remind myself, where the heck is that? Oh yeah. So the Hamiltonian for the spin orbit coupling involved the electric field which becomes a magnetic field in the frame of the electron. It's moving around with some speed. And then we have Ls. So now this we had before was a 1 over R potential for hydrogen, or hydrogenic atom. Now is the effective potential from the central field approximation. And so if I have a particular NL configuration, and this thing, of course, becomes J squared minus L squared minus S squared over 2. Then it turns out that under this, the central field can be expressed in terms of the quantum defect. And one finds the fine structure splitting in the alkalis, which typically would have gone like the charge of the nucleus to the 4th power, has the following kind of form. This is the fine structure splitting. In hydrogen, or hydrogenic, if I had a single electron, this form would be the charge of the nucleus to the 4th power divided by the principal quantum number squared. It gets modified in this approximate way in terms of now this kind of effective principal quantum number, n star. And then there is, it doesn't really go like z to the 4th because it depends upon how much the particular orbital has penetrated the core. So there's a kind of effective inner part of the nuclear charge and an outer part. I mean, to the degree to which Z in is on the order of, well, let's see, I'm confused. Because Z out, if I'm far away, should be like, oh yeah, no, Z out should be on the order of 1, and Z in is on the order of Z. This kind of goes like Z squared. So for example, in sodium, let's see. So in sodium, the D1 transition is at 589.6 nanometers, and this is 589.16 nanometers. And the fine structure splitting here is about 510 gigahertz. Okay. For cesium, in contrast, bad, erase this. For cesium, this is 852.35 nanometers. And 849, I forgot, does anyone remember what it is? I should know this.
894.5 or something?
The D1 line, no, it's 892, isn't it?
Is it?
Boy, I can't believe I don't remember that.
I thought it was like 894 or 895 for D1.
894 for,
For D1,
and D2 is
like 852. I don't know.
852, yeah. Okay, yeah, no, okay, that's right. Yeah, thanks, Ann. That's right.
This is for
This is
lithium or?
This is for cesium. That was for sodium, the standard isotope. This is the standard isotope of cesium. This splitting in this case is much bigger. You can see it's many nanometers, and in terms of frequency, the fine structure splitting is about 16.6 terahertz. So it's much bigger. It's huge. Moreover, the hyperfine structure is also bigger because that depends on, again, the speeds of the electrons because it's a magnetic effect. So in cesium, this ground state fine structure splitting is on the order of 9.2 gigahertz, and for sodium, it's 1.8 gigahertz.
Do you remember what I is for sodium?
Yes, I is 3 halves for sodium, the standard isotope, and for cesium, it's 7 halves. So in cesium, this is F equals 4 and F equals 3, and sodium, this is F equals 2 and F equals 1. Probably one of the most popular atom these days used in lots of these experiments is rubidium, because it's the easiest atom to make a Bose-Einstein condensate out of, and there are 2 different isotopes of rubidium that are stable, and they are rubidium 85 and rubidium 87, and they have spin 3 halves and spin 5 halves.
Why is rubidium so easy to make?
That has to do with the way in which you can evaporate the hot atoms out, and evaporate the cooling is the last step to Bose-Einstein condensation. Maybe we'll get there this semester. So it just turns out that the collision properties of rubidium are magical, and they just work out perfectly. They're in the Goldilocks regime. All right, excellent. All right, so this is our atomic structure. We're going to now think about manipulating these atoms, or studying the properties of absorption and emission of light in these atoms. And in order to do so, I want to return to the very basic description of the interaction of charges and fields. Okay? So we're going to study absorption and emission. Let's begin with the fundamental Hamiltonian. What do I mean by that? Well, what's often called the minimal coupling Hamiltonian, which one can derive from a fundamental Lagrangian for charges interacting with electromagnetic fields, would say the Hamiltonian would be the following. Have the sum over all the particles, the kinetic energy depends on the canonical momentum and the vector potential. And then I have the interaction potential between all the charges. I have the interaction of the charges with the scalar potential. And then I have the effect of the intrinsic spin, which is not part of the classical Lagrangian, but comes sort of extra. And that would then be minus the sum over all the intrinsic spin magnetic moments if they have spin angular momentum interacting with the local magnetic field. Okay, so this is the fundamental Hamiltonian where phi and A are the scalar and vector potential of the applied field. Whatever field in it, other than the intrinsic field of the charges themselves, if I'm shining light on the system, or I'm putting a magnetic field on the system, or I'm putting a microwave on the system, the A and phi are the scalar and vector potential associated with those fields. Okay. Now, this form of the Hamiltonian, while correct, is not the most convenient form to work with. The reason is that what we have in our problem wavelength of the applied wave, say if we're applying an electromagnetic wave to the system, is typically much, much bigger than the Bohr radius. So the Bohr radius represents the scale of the size of the charge distribution of the atom. And we're applying a field which has a wavelength which is, say, a half of a micron. In that case, it's convenient to think about the interaction, as you remember from your electromagnetism, in terms of a multipole expansion. And while one could do that directly in the minimal coupling Hamiltonian, it's not a very nice way to look at the problem. So one can reformulate this in a form that's natural for thinking about a multipole approximation by making a gauge transformation. So let's remind ourselves about gauge transformations. So under a gauge transformation, by the way, this is all in CGS units, so that's why there's a lens VLI here, if you're less familiar with that. Under a gauge transformation, I have a gauge function. And I can change my definition of the vector potential and my definition of the scalar potential notice in CGS units, A and phi have the same units. Well, no, this is not correct, but this is. If I make such a transformation for an arbitrary gauge function chi, I do not change the physical forces. E and B are the same. So a convenient gauge transformation is the following. We can make such a gauge transformation that corresponds to a unitary transformation on the Hamiltonian, and then on the state vectors. As you may remember from your quantum mechanics, I can do a gauge transformation. It corresponds to a different picture. It means I've done a unitary transformation on everything, changed all the basis vectors by a unitary transformation, made a unitary transformation on my observables, and it doesn't change. It's like going from the Schrodinger picture to the Heisenberg picture. In the end, I can do it either way. So I do that in quantum mechanics with a unitary transformation for a real function chi. That's a unitary operator acting on the space. If I do that, if you go back and you look at, go into your favorite quantum mechanics textbook, that accomplishes this gauge transformation. Okay. So what's the gauge function we're going to take? The current, this is written as it's written here. It's written in the Coulomb gauge, which is to say I've chosen A dot 0. So all of the longitudinal part of A is in this potential. That's kind of the quasi-static potential. And A basically represents the radiation, which has both magnetic and electric fields. So one can make what's called the power transformation. By choosing the following form, having a new gauge where I choose chi, to be equal to minus r sub I dotted into the original A. when I do so, let's see, firstly, it's easy to take the time derivative of this. So 1 over c d chi dt is equal to yeah, I guess the way I define this, that I put the charge inside here. That's right. So 1 over c d chi dt is minus qi r sub I dotted into minus 1 over c dA dt. And you remember that that's just the electric field. Okay. Everyone remembers everything about UNM, right? Right. Come to 511 next semester. Let's see, the gradient of this is equal to r sub I crossed into the gradient with respect to the I coordinate, sum over I, curl of A plus r sub I dotted into the gradient acting on A.
Now that's R sub I, meaning the ith electron,
That's right. Or charge.
or charge, right? And then the gradient is in the ith component, meaning x, y, and z.
No, this is on the ith coordinate.
Oh,
Yep, that's what that means. I'm sorry, but that's what I mean.
fair enough.
Okay, so what do we see when we put this all together? Oh no, I'm sorry, plus, minus, this goes, there's a minus, everything's got a minus, there's a minus sign over everything. Minus A. That's what happens. You gotta, go through and take the gradient, for a particular coordinate, I'm looking at this. And then there's a funky formula with, you can do it with tensor notation, whatever. You gotta do it, it's not fun, but. The bottom line is this. When I put that together in this new gauge, I have the following. I have the original atomic Hamiltonian, looking at the interaction, the kinetic energy of all the charges and the Coulomb interaction between all the charges. This term combines with that term to look like the following, plus some Q sub I, whatever the initial potential that was addressed, minus R sub I dot E sub R sub I and T. That's this term. We're going to subtract out that. And then all this other mess. Now the other mess is a real mess because there's this combination of what you may remember of diamagnetic and paramagnetic interactions of fields with moving charges. So I'm going to push that all under the rug and just say it has the following form. diamagnetic terms really have nothing to do with absorption and emission. They have to do with really Z interaction. But we have this form where mu I is equal to qi over 2I to the minus c Li plus G sub S sub I. So I have times the more magnetic. So I have an orbital contribution to the magnetic moment, depending on the orbital angular momentum of the I particle, with a factor here that's the usual gyromagnetic ratio. In addition, I have spin. And this could also involve the nuclei. There'll be another term for the nucleus. Okay, let me just conclude this by now looking at this expression and making some sense of it. What I have here is, I've broken this up now in terms of the Hamiltonian of the atom that we had originally in the absence of this external field, and then terms that have to do with the interaction of the atom with the external fields, which involves interactions with the electric field and the magnetic field. How do I interpret these terms? Well, for fields varying slowly respect to the size of the atom, my interaction terms, I can do a multipole expansion. In terms of the distribution of electrons. And my interaction potential then looks like the following. So let's conclude by just examining what this means. Let me actually say my field runs somewhat picture. What I see is a term that has to do with the monopole moment. a term that has to do with the electric dipole moment. A term that has to do with the electric quadrupole moment. A term that has to do with the magnetic dipole moment of the atom, etc. And so by expressing things this way, what I see is different interaction terms that involve, oh, this should be a minus. It's important. That's actually there, that minus sign. I have a term that looks like the total charge of the atom. Well, of course, if this is a neutral atom, this is 0. But if I have an ion, I can trap that ion by applying an external potential. But that only affects something about the internal. So, I'm sorry, R is the position of the nucleus, which is essentially the center of mass of the atom. And then we have different multipole moments that have to do with the relative coordinate of the electron relative to the nucleus. We have something that has to do with the electric dipole moment interacting with the electric field at the center of the atom. We're ignoring the variation in this approximation. We then have something which has to do with the gradient of the electric field across the atom. That is not a big term, generally. But if this term is 0, we need to worry about this term. And that has to do with the electric quadrupole distribution of the charges relative to the nucleus. And we have also magnetic effects.
Is H diamagnetic on the same order as U dot B?
It is, except it's really it depends what we mean by the order. It has no effect on the transition rates. It has an effect on the shifts and the perturbations of those levels. Because it's not a resonant effect.
And is this big R in the position of the nucleus only in heavy atoms? Like, is it really the center of mass, or is it really the nucleus?
It's really the center of mass.
Okay. So like for positronium.
So if I had a positronium, it would be different. Yeah. But in the context of regular matter, we ignore that small assumption. Okay. So just to conclude, let me just say the point of this, as we see, is that the different moments of the distribution interact with the fields. And the strength of the interaction will depend on the strength of these different terms. What we're going to do, and what I would urge you to do for next lecture, obviously this kind of description requires us to think about tensors in quantum mechanics, because we got the quadrupole tensor, we got vectors, and we need to think about tensors in quantum mechanics. So, if you've studied tensors in quantum mechanics and the Wigner-Eckhart theorem, now is the time to review that. We'll do it again next time. All right? Have a good rest of your day, except for those of us who will see each other in 5-10 minutes.